Welcome to Wormhole to Cosmos, where we take you beyond the stars and into the next frontier of space exploration. Ladies and gentlemen, embark with us on an extraordinary journey as we delve into Firefly Aerospace's Blue Ghost Mission 1, aptly named Ghost Riders in the Sky. This mission signifies a monumental leap in our quest to explore and comprehend our celestial neighbor. Our voyage begins with an in-depth look at our destination, Mare Crisium, a vast lunar basin that holds secrets waiting to be uncovered. We'll then explore our spacecraft, the Blue Ghost Lander, a marvel of engineering, equipped to navigate the challenges of space travel and lunar surface operations. Next, we'll delve into the suite of scientific payloads aboard Blue Ghost, each designed to unravel the Moon's mysteries and pave the way for future exploration. Following this, we'll provide a comprehensive mission summary, detailing each critical phase from launch to lunar landing. Finally, we'll examine the descent phase, where precision and technology converge to ensure a safe touchdown on the Moon's surface. Together, we'll witness how this mission not only enhances our understanding of the Moon, but also brings us closer to establishing a sustained human presence beyond our home planet. Mare Crisium, a name that whispers tales of ancient cosmic events and human ambition. Nestled in the northeast quadrant of the Moon's near side, this Sea of Crises is not a sea at all, but a vast lunar basin spanning an impressive 740 kilometers across. Born in the Nectarian period over 3.9 billion years ago, it is a timeless witness to the Moon's volcanic and geological history. Thanks to data from the Lunar Orbiter Laser Altimeter, or LOLA, we've come to understand Mare Crisium with stunning precision. Picture this. Its floor lies an astonishing 1.8 kilometers below the Moon's sea level, or lunar datum, while the outer rim towers 3.34 kilometers above it. Imagine standing on that rim, peering across a landscape sculpted by ancient lava flows, so prominent they're visible even in modern topographic data. These flows, frozen in time, are the Moon's own brushstrokes on a canvas of basalt. But this mare isn't just a geological marvel, it's a cornerstone of human and robotic exploration. Back in the 1960s and 70s, two Soviet missions dared to touch this alien ground. Luna 24 landed gracefully in 1976, successfully returning samples of lunar regolith to Earth, a feat that brought us closer to unraveling the Moon's secrets. Its predecessor, Luna 15, wasn't so fortunate. In 1969, as the Apollo missions captivated the world, Luna 15 crash-landed in Mare Crisium, leaving a poignant reminder of the challenges of space exploration. This lunar basin has also found a place in the realm of imagination. Fans of science fiction might recall, the Moon is a harsh mistress, where Mare Crisium is home to the fictional Luna City, a vision of humanity's future among the stars. And now, in the present day, Mare Crisium is preparing to host yet another chapter of exploration, Firefly Aerospace's Blue Ghost Mission 1. As this pioneering lunar lander descends onto its surface, it will carry not only instruments of science, but the weight of history and the dreams of a species ever curious about its place in the cosmos. From ancient lava flows to literary lore, Mare Crisium stands as a testament to our enduring fascination with the Moon, a celestial neighbor that still beckons us to explore, discover, and imagine. Introduction to our payloads. The payloads aboard Blue Ghost Mission 1 are more than just instruments. They are stepping stones toward the future of lunar exploration. These scientific tools will push the boundaries of our understanding, conducting first-of-their-kind demonstrations in regolith sample collection, global navigation satellite system navigation, radiation-tolerant computing, and lunar dust mitigation. Each payload is designed to gather data that will not only shape the next era of spaceflight, but also provide crucial insights for life here on Earth. From understanding space weather to testing new technologies for planetary exploration, these experiments will pave the way for humanity's return to the Moon. Now, let's take a closer look at each one. Lunar Interior Temperature and Surface Heat Flow Experiment, LISTER. The Lunar Interior Temperature and Surface Heat Flow Experiment, LISTER, is designed to measure the heat flow from the Moon's interior, providing critical insights into its thermal history, geological evolution, and subsurface composition. By penetrating 2 to 3 meters beneath the lunar surface, LISTER will help scientists determine how heat escapes from the Moon's core and travels through the regolith and rock layers. LISTER's heat flow analysis relies on 2 key measurements: thermal gradient, how temperature varies with depth, revealing the rate of heat loss from the interior; thermal conductivity, how efficiently heat is transferred through the lunar material, offering insight into its composition and structure. This data will be collected using a pneumatically drilled subsurface thermal probe capable of conducting 5 separate measurements at different depths. These readings will help refine our understanding of the Moon's internal heat flow, which is essential for modeling its formation, volcanic activity, and long-term surface conditions. LISTER's findings could also have implications beyond the Moon, helping researchers study the thermal dynamics of other planetary bodies. Developed by Texas Tech University under CLPS Task Order 19D, this payload, led by Dr. Seiichi Nagihara, will provide key data for future lunar exploration, planetary science, and potential lunar habitat development. Stereo Camera for Lunar Plume Surface Studies, SCALPSS 1.1. The SCLPS 1.1 payload is an enhanced version of the original SCLPS system, previously deployed on Intuitive Machines' IM-1 mission. Designed to capture video and still image data of the lunar surface before, during, and after the lander's descent engine plumes interact with the Moon, SCLPS 1.1 provides critical insights into how lunar dust is displaced during landing, a key factor in lander safety, surface erosion, and spacecraft design. This upgraded version features 2 additional cameras optimized to begin capturing images from a higher altitude before the expected plume surface interaction, PSI. Using stereophotogrammetry, SCLPS 1.1 will generate high-resolution topographical data, allowing scientists to measure total erosion and crater volume before and after PSI, analyze the rate of surface morphology changes caused by engine plumes, validate computational models of PSI effects, which are essential for the design and risk assessment of future lunar landers. The transient data collected while PSI is occurring will provide real-time information on the speed and dynamics of regolith displacement, helping engineers refine landing procedures and thruster designs to minimize dust hazards for future missions. SCLPS 1.1 is based on the Entry, Descent, and Landing Camera Suite, EDL, used on NASA's Mars 2020 mission, which provided detailed visual data of the Martian surface during landing. This technology, now adapted for the Moon, will support the development of safer, more precise landing techniques for larger spacecraft. Developed by NASA Langley Research Center, LARC, under CLPS Task Order 19D, this payload, led by Michelle Monk, will play a crucial role in advancing safe and efficient lunar landings, ensuring that future missions can land on the Moon with greater precision and minimal disruption to the surrounding surface. Lunar Planet Vac, LPV. The Lunar Planet Vac LPV is a pneumatic-based regolith sampling system designed to collect and transfer lunar soil for scientific analysis. Unlike traditional scooping or drilling methods, LPV uses compressed gas to lift lunar regolith and transport it to onboard instruments for examination. This technique offers a fast, efficient, and contamination-free way to gather samples from the Moon's surface. Mounted on one of Blue Ghost's footpads, LPV consists of 3 key subsystems. Sampling head, pressurized gas jets blast the surface, lifting dust and soil into a suspended cloud of regolith. Transfer tube, a secondary set of gas jets, propels the material up the tube toward collection. Sample container. The regolith, up to 1 centimeter in size, is sieved, photographed, and stored for further analysis. This fully autonomous system completes sample collection in just a few seconds, requiring no human intervention. LPV's pneumatic method minimizes wear and tear on the lander while ensuring that pristine, uncontaminated samples are delivered for study. LPV has broad applications beyond the Moon, as it can be used for future missions to Mars, asteroids, and other celestial bodies. Developed by Honeybee Robotics under CLPS Task Order 19D, this payload, led by Dr. Chris Zacny, will demonstrate next-generation sample collection techniques, helping to shape the future of planetary exploration and resource utilization. If you're enjoying this journey, subscribing really helps us out, and we'd love to have you along for more explorations. And if you're excited about space, give us a thumbs up. It lets us know you want more videos like this. Radiation-Tolerant Computer, RAD-PC. The Radiation-Tolerant Computer, or RAD-PC, is a technology demonstration designed to withstand the harsh radiation environment of space. Using a Field Programmable Gate Array, FPGA, it implements fault mitigation strategies to recover from single event effects, SEEs, caused by ionizing radiation. By leveraging commercial FPGA technology, RAD-PC balances radiation tolerance, power efficiency, and performance. On board, a comprehensive test program continuously monitors its state of health, ensuring its resilience against space radiation. To support this experiment, 3 dosimeters, each tuned to different sensitivity levels, will collect radiation energy level data, helping correlate environmental conditions to RAD-PC's performance, while also mapping the radiation levels at the lunar landing site. Developed by Montana State University under CLPS Task Order 19D, this payload, led by Dr. Brock J. Lemires, is a crucial step in developing radiation-hardened computing systems for future deep space exploration. Lunar Environment X-ray Imager, LEXI. The Lunar Environment X-ray Imager, LEXI, is a wide field of view, soft X-ray imager designed to observe how energy from the solar wind interacts with Earth's magnetosheath and magnetopause. These interactions play a crucial role in generating geomagnetic storms and space weather, phenomena that can impact everything from satellite communications to power grids on Earth. LEXI detects soft X-ray photons in the 0.1 to 2 kilo-electron-volts range, emitted when high-energy solar wind ions collide with neutral particles in Earth's exosphere. By capturing these charge exchange interactions, scientists will gain new insights into how the solar wind transfers energy into Earth's space environment. This research builds upon previous findings from NASA's Themis mission, further improving our understanding of Earth's magnetosphere and its protective role against space radiation. The instrument is equipped with 9 lobster-eye micropore optical elements, mounted on a single plate with a 75-centimeter radius of curvature, allowing it to image the magnetopause with a broad field of view. This innovative design will provide detailed visualizations of the boundary regions where Earth's magnetic field meets the oncoming solar wind. Developed by Boston University under CLPS Task Order 19D, this payload, led by Dr. Brian Walsh, will contribute vital data for space weather forecasting, planetary magnetosphere research, and future deep space exploration, helping to protect both astronauts and technology beyond Earth's atmosphere. Lunar GNSS Receiver Experiment, LUGRE. The Lunar GNSS Receiver Experiment, LuGRE, is a groundbreaking technology demonstration designed to test Global Navigation Satellite System, GNSS-based spacecraft navigation during transit to the Moon and on the lunar surface. By leveraging Earth-based GNSS signals, LuGRE aims to enable real-time positioning, navigation, and timing, PNT, on and around the Moon, a capability that could significantly reduce reliance on traditional ground-based tracking networks. Mission objectives. LuGRE, a collaboration between NASA and the Italian Space Agency, ASI, will achieve three primary goals: receiving GNSS signals at the Moon and analyzing the signal environment at lunar distances well beyond GNSS systems' original design, demonstrating onboard navigation and time estimation using GPS and Galileo satellite data collected during lunar operations, advancing the development of lunar-specific GNSS receivers, paving the way for a future lunar GPS network to support sustained human and robotic exploration. Technology and implementation. Type of instrument: a weak-signal GNSS radio receiver equipped with a 14-decibel isotropic high-gain antenna and a low-noise amplifier to enhance signal reception. Key measurements. LuGRE will track GPS L, 1CA, and L5 bands, as well as Galileo E1 and E5A bands, collecting data on signal strength, stability, and usability at lunar distances. LuGRE is a step toward building a lunar navigation infrastructure that could one day guide astronauts, landers, and rovers across the Moon's surface, just as GPS does on Earth. Developed by NASA's Goddard Space Flight Center, GSFC, under CLPS Task Order 19D, with Joel Parker as the principal investigator, this experiment is a critical first step in establishing a lunar GNSS system to support future Artemis missions, lunar habitats, and beyond. Regolith Adherence Characterization, RAC. The Regolith Adherence Characterization, RAC, experiment will determine how lunar regolith adheres to different materials when exposed to the Moon's environment throughout the lunar day. Its purpose is to help scientists develop better protection for spacecraft, spacesuits, and habitats against abrasion caused by lunar dust. RAC carries 30 material samples, including thermal control paint, Captain, titanium, and a dust collection disc provided by NASA and industry. These samples are arranged in two identical rotating wheels, A and B, which cycle into view of cameras every 24 hours for imaging. Wheel B, which remains covered until post-landing commissioning is complete, serves as a control against transit effects on Wheel A, which remains exposed for the entire mission. RAC will also quantify the accumulation rates of regolith caused by the lander's arrival and routine operations. To enhance its scientific findings, RAC will collect infrared IR, ultraviolet UV, and temperature data, augmenting the science return of its 5.1 megapixel images. Operations are autonomous with limited ground control access for recovery and contingency. Components of this experiment are derived from the Materials International Space Station experiment, MISSE, previously used on the International Space Station, ISS. RAC is classified as a dust collector detector with a key measurement of accumulation rates of lunar regolith on multiple surfaces, including solar cells, optical systems, coatings, and sensors, to determine their ability to repel or shed lunar dust. Developed by Aegis Aerospace, Incairns, under CLPS Task Order 19D, this payload, led by Matt Carter, will provide crucial data on lunar dust behavior, influencing future spacecraft and habitat designs for upcoming Moon missions. Electrodynamic Dust Shield, EDS. Lunar dust is a major challenge for spacecraft, equipment, and human missions, clinging to surfaces and posing risks to both hardware and astronaut safety. The Electrodynamic Dust Shield, EDS, is an active dust mitigation technology designed to tackle this problem by using electric fields to lift, transport, and remove dust without moving parts or consumable materials. For the first time, EDS will be tested on the lunar surface, demonstrating its ability to keep glass, thermal radiators, and other critical surfaces clean. In addition to removing dust, the EDS will test a new reduster technology, which can lift and transport lunar regolith to targeted surfaces, offering potential applications for future lunar construction and resource utilization. How it works. EDS uses electrostatic forces to repel and clear dust from surfaces. The system will be deployed from a fifth leg of the Blue Ghost lander, maximizing direct contact with the lunar surface. 2 EDS units will be tested, one for a small camera mounted under the lander's deck, ensuring a clear view for imaging, another on a white aluminum panel on the lander's footpad, evaluating performance on different materials. High-resolution imaging will document the dust removal efficiency, providing crucial data for future dust mitigation designs. Developed by the Electrostatics and Surface Physics Laboratory at NASA Kennedy Space Center, KSC, under CLPS Task Order 19D, this payload, led by Charles Buhler, will help shape self-cleaning technologies for lunar habitats, spacecraft, and scientific instruments, an essential step toward long-term lunar exploration and survival. Lunar Magnetotelluric Sounder, LMS. The Lunar Magnetotelluric Sounder, LMS, will measure natural electric and magnetic fields to determine the electrical conductivity profile of the Moon's interior. This data will help scientists understand the Moon's thermal structure, geologic history, and subsurface composition. How it works. LMS detects time-varying fields from the solar wind and Earth's magnetosphere. By analyzing how these fields interact with the lunar surface, researchers can map subsurface conductivity, revealing temperature variations and material composition. Key science goals: determine the Moon's internal temperature structure and cooling history. Compare Mare Crisium to the Apollo landing sites to identify regional differences. Enhance models of the Moon's evolution and subsurface composition. Technology and implementation instrument. Type, electrometer, and magnetometer, using technology from MAVEN, THEMIS, and MSLRAD. Key measurement, the ratio of electric and magnetic field spectra, allowing scientists to calculate depth-dependent conductivity. Developed by Southwest Research Institute under CLPS Task Order 19D with Dr. Robert Grimm as the principal investigator, LMS will provide critical data for future lunar exploration and resource utilization. Next Generation Lunar Retroreflector, NGLR. The Next Generation Lunar Retroreflector, or NGLR, is a precision instrument designed to measure the exact distance between the Earth and the Moon. Using laser pulses sent from Earth-based lunar laser ranging observatories, NGLR will reflect those signals back, allowing scientists to measure the transit time with extreme accuracy. The original Apollo-era retroreflectors provided the fundamental lunar coordinates we still use today, but NGLR will take this even further, offering sub-millimeter range measurements. This will refine the lunar coordinate system, supporting future missions under the Artemis program. But its significance doesn't stop there. NGLR will advance our understanding of lunar physics, astrophysics, and even cosmology. By measuring how the Moon's core deforms over time, we gain insight into its internal structure. It will also help address fundamental questions about dark matter by tracking the Moon's precise motion over long periods. This instrument, classified as a cube-corner retroreflector, is mounted securely on the lander, ensuring stability for long-term data collection. Its key measurements include the oblateness of the lunar core, elastic tides and lunar tidal dissipation, the boundary between the Moon's core and mantle, lunar cartography and free physical librations, and even gravitomagnetism, offering insights into the subtle effects of gravity in our solar system. Developed by the University of Maryland under CLPS Task Order 19D, this next-generation retroreflector, led by Dr. Douglas Curry, will support the Lunar Laser Ranging Program, ensuring we continue to refine our understanding of the Moon, Earth's only natural satellite, for years to come. Our ride, Blue Ghost Lander. Structure and design. Standing at 2 meters tall and spanning 3.5 meters wide, Blue Ghost is built for stability. With shock-absorbing feet, a low center of mass, and a wide footprint, this lander is designed to handle the rugged lunar surface with ease. Its core components, panels, struts, legs, harnesses, avionics, batteries, and thrusters, are built on the same flight-proven technologies found in Firefly's launch and orbital vehicles. That means lower costs, greater reliability, and a spacecraft engineered for success. Mission support. Throughout its 60-day mission, during lunar transit and surface operations, Blue Ghost will supply power, thermal resources, and data support for its suite of scientific payloads. Reaction Control System, RCS, thrusters. Firefly's engineers designed and built 8 in-house reaction control system, RCS thrusters, known as Spectre. Together, they produce 1,600 newtons of total thrust, maintaining orientation during critical maneuvers and throttling for a smooth, controlled lunar landing. Attitude Control System, ACS. Thrusters. With a legacy of 5 successful flights on Firefly's Alpha rocket, the lander's 12 cold gas attitude control system, ACS thrusters, provide precision pointing through all coast phases and deliver settling thrust before each maneuver. Main engine. Blue Ghost's main engine generates more than 1,000 newtons of thrust, playing a vital role in lunar orbit insertion and the all-important braking burn before landing. Landing legs. Constructed in-house using Firefly's lightweight carbon composites, the lander's 4 legs are built to handle the Moon's challenging terrain. Crush-core honeycomb structures absorb impact forces during touchdown, while footpad sensors detect ground contact, triggering the engine shutdown sequence. Communication antennas. Communication is key. Blue Ghost is equipped with 1 X-band antenna and 3 S-band antennas, ensuring a robust link between the lander and Firefly's Mission Operations Center in Texas. This system enables real-time data transmission and high-definition video from the Moon. Solar power generation. 3 solar panels, 2 on the sides and 1 on the top deck, provide up to 400 watts of power. Over the course of the mission, these panels will generate a total of 1,470 hours of power for both the lander and its 10 onboard payloads. Structural integrity. Struts. Strength and durability are essential for any spacecraft venturing to the Moon. Blue Ghost's frame is reinforced by 49 high-strength, lightweight carbon composite struts, the same technology used on Firefly's launch vehicles, ensuring a rigid structure that supports payload operations with maximum efficiency. Propellant tanks. 2 helium pressurant tanks and 4 propellant tanks wrapped in carbon fiber store the lander's supply of MMH fuel and MON3 oxidizer, critical components for propulsion and controlled descent. Navigation cameras. The final moments before landing demand absolute precision. Blue Ghost's 2 vision navigation cameras scan the terrain, identifying potential hazards and pinpointing the safest location for touchdown. Because when it comes to landing on the Moon, there are no second chances. Keep watching, because we're not done yet. From our family to yours, we truly appreciate your support. If you enjoyed this journey, subscribe to Wormhole to Cosmos. It helps us create more videos exploring the wonders of space. And don't forget, March 2nd marks the historic landing of Blue Ghost on the Moon. But now, let's take a look at how it all unfolds. From launch to landing, here's what we can expect when Blue Ghost embarks on its journey to Mare Crisium. Blue Ghost Mission 1 Ghost Riders in the Sky is a milestone in lunar exploration under NASA's Commercial Lunar Payload Services initiative. On January 15, 2025, at 1:11 a.m. Eastern Standard Time, Blue Ghost launched aboard a SpaceX Falcon 9 rocket from Kennedy Space Center. 66 minutes later, it separated from the rocket and established communication with Firefly's Mission Operations Center in Cedar Park, Texas. Over the next 25 days, engineers conducted subsystem health checks, verifying each component before payload operations began. Scientific instruments were powered on, collecting preliminary data in preparation for the Moon's environment. After all systems were confirmed operational, Blue Ghost executed trans-lunar injection, sending it on a 4-day journey to the Moon. Upon arrival, the lander performed a deceleration burn, placing itself in lunar orbit for 16 days of final checks and calibration. At L-63 minutes, Blue Ghost initiated its descent toward Mare Crisium, coasting from 100 kilometers down to 20 kilometers before firing its engines to slow from 1.7 kilometers per second to 40 meters per second. At 500 meters altitude, the main engine shut off, and reaction control thrusters guided the lander through hazard avoidance maneuvers, ensuring a safe landing site. In the final 10 meters, Blue Ghost descended at 1 meter per second, touching down on shock-absorbing legs, with footpad sensors signaling engine shutdown. With a successful landing, Blue Ghost began its 14 Earth Day surface mission, operating 10 NASA instruments designed to study lunar regolith, geophysical characteristics, and solar wind interactions. Instruments measured radiation levels, temperature variations, and dust accumulation, providing crucial data for future missions. As the lunar day ended, the lander captured high-definition images of the lunar sunset, continuing operations into the early lunar night, pushing the boundaries of current lunar exploration capabilities. This mission demonstrates precision, technology, and innovation, paving the way for humanity's return to the Moon and future deep space exploration. Thank you for watching. I truly appreciate it. If you enjoyed this video, let me know in the comments. We can definitely create a more in-depth look at anything that caught your interest. And of course, subscribe to Wormhole to Cosmos so you don't miss future explorations. We'll see you next time.